Kia ora, Robert McLaughlin here, and welcome to week 12, lecture 2 of differential equations. In the last lecture we looked at Euler's method for systems of differential equations, and the drawback of Euler's method was that it wasn't very accurate, so we want a better method. So let's try and derive a better method. And we can do that with a sort of a graphical method, thinking of the example when the phase spaces are 2. In Euler's method, we started at x0, we calculated the vector field at that point, which was f at x0, just do the autonomous case for now, and we took a step in that direction. To get to here. And the problem was the vector field has changed direction, so that the true solution is going to curve away a bit like that. Let's call that the true solution, x as a function of t. And that's my error. So what can I do about it? The idea is the following. Take the Euler approximation and evaluate the vector field at that point. Now that's going to be pointing in a slightly different direction. A bit like that. And the average direction I should have chosen is roughly equal to the average of those two vector fields. So instead of using the direction I'm traveling at the start or the direction I'm traveling at the end, the idea of the method I'm going to write down in a second, which is called the improved Euler method, is to take the average of those two. So in this example, it's a bit hard to draw, isn't it? But it'll give me something that is roughly like going in about this direction to about there. Tempted to take the average of the two blue arrows and go in that direction, and that will be much closer. Now, of course, the real best thing to do would be to take lots and lots of points along that correct. Is that purple? It's not really a sort of a purpley red, reddish purple. Average of all of the vectors along that correct track, but that would be even more accurate again. But the average of the start and the end is not too bad. So what's the formula for that? That's going to be first compute a vector k1. That will be my vector field evaluated at x0 and t0. Actually, I'll write xn and tn. That's my initial blue arrow. Then I get a second direction, which is going to be my vector field evaluated at a new point. What's the new point? Well, it's the Euler approximation. That's this guy here. So that's xn plus hk1. And what time should I be at there? Well, I should be at the new time, which is tn plus h. So now I've got my two arrows called k1 and k2. And I want to update x using the average of those, but still with step size h. So altogether, this is called the improved Euler method. And the theoretical result on the error, the norm of the exact value, which is x at tn, minus the approximation, xn, is approximately equal to some constant times h squared. In other words, it's proportional to the step size squared. And that's much better than being just proportional to the step size. That means when I make the step size 10 times smaller, the error doesn't get 10 times smaller, it gets 100 times smaller, and that's much better. So let's try that out now in Octave. Here's my code. And the nice thing is it's very, very similar to the code for Euler's method. Once you know the idea of the method, it's very easy to program it up. So here we have going from time 0 to time 0.4, n steps equals 8. Compute the step size, the initial condition, K1 computes the vector field at the current point. K2 computes the vector field at the Euler approximation, so x plus h k1 tn plus h, and then update using the average of those two. So it's really only one more line compared to the Euler code. So getting in a huge improvement in accuracy for one extra line of code, that's pretty good. So let's try it out. The program's called Improved Euler. In steps is hard-coded in at 8. Improved Euler. There we go, 0.88333. And I still have my variable saved in before. It was saved in exact. The exact value for y, the final y, was 0.88396. So I've already got almost three decimal places of accuracy just within steps equals 8. Let's look at the error. I'll change my code so that the number of steps is no longer hard-coded in. In steps equals 8. Call improved Euler. And now I'm going to print out the error, which is exact minus x transpose. There we are. The error is 0.0006. And if I repeat it within steps equals 16, now the error is 0.00016. So it's gone from 00063 to 00016. That's a factor of 4 smaller. So when I halve the step size, the error reduced by a factor of 4. That's much better. That should do it again. I go in steps equals 32. To print out, the error is now 0.00. How many zeros? 0.00004. Again, factor of 4 smaller. So already getting down to almost four decimal places correct. So that's very good. Now that was a very easy improvement to make, both to derive the method and to implement it. And the accuracy improvement was startling. So the obvious question is, can we take this idea and generalize it? And we can. And the method of doing that leads to a whole class of numerical methods called the Uranga methods. It's not just one numerical method, it's a whole family, and different versions of this family are used for different purposes, depending on your differential equation and depending on how accurate you want. And one of these is built into MATLAB as the ODE45 method. So what's the idea? Well, initially I was starting here, and if I'm starting here, all I can really do is evaluate the vector field at that point. And from that, it seems that all I can really do is take a step in that direction, and that'll give me some other approximation, and then I could evaluate the vector field there. But now I've got two directions, just like I had with improved Euler. I could take a step in some linear combination of those two directions. I could head out this, since an average of those looks good, I could head out in the average direction for a certain distance, and then I could evaluate the vector field there. So each time I take a step using the information that I've gained so far, I can combine all of that to get a better approximation. So what would that look like? Well, for the first step, I would just evaluate the vector field at xn and tn. For my next vector field, I could evaluate it at xn plus some constant. I'll just call the constant a1. Some multiple of that direction. Tn plus some constant. I'm not going to worry about too much about what those numbers are. They're just numbers that I'm going to choose. And then for the next step, I have more choices. This is the key point. Because now I could go xn plus a3 hk1 plus a4 hk2. And similarly for the times, I could go k4, again using some linear combination of the three previous ones. I could do as many of these as I want. And the question now is, How do I choose these parameters to get the most accuracy for the given work? Once I've computed all these directions, they're all going to be very similar to each other. They're all pointing roughly in the direction of the vector field. Then I make my update step as a linear combination of them. C1 K1 plus C2 K2 plus dot dot dot. So how accurate can you get for a given number of vector field evaluations? If you just use one evaluation, that's basically Euler's method. And then the error we have seen is proportional to h. We also did a method with two evaluations of f. That was the improved Euler. And there we found that the error was proportional to h squared. And that was the motivation for doing the more general thing. So that leads to an obvious question. What's the best you can do for a given number of vector field evaluations? Now it turns out the complexity does rise in a rather scary way, and you sort of need to make a bit of a balance or a compromise. But there's a method that I'm going to call fourth order Uranga cutter, RK4. It has 4 evaluations of f, and the error is proportional to h to the 4. Now there's a pattern there, but unfortunately that pattern doesn't hold anymore. A New Zealand mathematician, John Butcher, who's still alive and going well, is in his mid-80s. He, starting in the 1960s and for many decades thereafter, he did a revolutionary study of Uranga cutter methods, proved all sorts of results and discovered all sorts of new methods that are in wide use today. And I believe it was him who proved that a fifth order method, so where the error is proportional to h to the 5, needs at least 6 evaluations of f, not 5 as you might have guessed. So what is this Uranga cutter for? It's a really commonly used real workhorse method. Let's write down what that looks like. K1 is f of x in just f of x in t in. K2 is f of x. Now I take a sort of a half step in the K1 direction. Then I do a sort of another half step, but in the K2 direction. Each time I evaluate the vector field, I'm getting a little bit more information about how it's changing direction close to the current point. And now for K4, I take a whole step in the K3 direction. So now I've got my 4 evaluations of the vector field at 4 nearby points. Then I update my x, and I do a weighted average of all of those k's. And the formula is K1 plus 2K2 plus 2K3 plus K4. Again, quite a nice simple formula. And the error is proportional to h to the 4, which is very good. That means if you reduce the step size by a factor of 10, the error should go down by a factor of 10 to the 4, which is pretty good, 4 more decimal places of accuracy. So if you need many decimal places, like it would be common to want to have at least 8 or 10 decimal places, if you could, then a method like this would be the method of choice. Let's see what the MATLAB program looks like. Here it is. I've called it RK4.m, great imagination. Very little of the code has changed. This is the meat of it here, K1, K2, K3, K4, and those formulas that I've typed into MATLAB, they look very, very similar to the mathematical formulas that I wrote down earlier. Call the vector field 4 times, update the x's with the weighted sum, and you're done. Let's comment out the end steps so that I can immediately start using my program interactively. The other nice thing to note is that once this program is written, this will work for any differential equation, right? Because I just need to change the function f that specifies the differential equation. Here we go. So in steps equals 4, run RK4. 0.88396. Wow. So even with 4 steps, I've got the 883 correct. I've got the 8839 correct. So I've got 4 decimal places correct just with 4 steps. That is pretty good. Let's do that again and look at the error. Exact minus x transpose. There's the error. Wow, so many zeros. There is like 10 to the minus 5 already. That shows, well, that shows the value of a little bit of theory. Now, there's one more question you might have in your mind, which was where did those special coefficients come from for the K1, K2, K3, K4? Well, that does require a bit of calculus and algebra. How that was done was by expanding the exact solution and the approximation in Taylor series and matching them up, choosing the coefficients so that they would match up very accurately to each other. It's a nice piece of work.